looking for. My question was a little bit simpler, and maybe today restarting, and we will restart with a very brief recap of what we discussed during the last terrible lectures before going to apply those expressions to understand the focal mechanism representation, what we call the beach balls. So we will result from that, and I will try to ask you what is the origin of, okay, good morning. So I'm going to ask you what is the origin of a time derivative when we consider the double couple. So, okay, I think we can start now. Again, let me try to be, so what about the audio that you're getting from me? Is it acceptable?
Yeah, it's good.
Okay.
I think it's good than even the last time we met.
So you don't like my university? That's the point. Oh well, this is the university.
No,
but
I think when it's good than when we were in the Stasi room. The audio.
Okay, not part of that. Okay.
Yeah.
Okay, let's try to do our best. As I told you, I have to try to be continue with at the end of the lecture. Okay. But okay, let's hope. Okay, let me share my screen and let's start again from this new lecture and what we are going to do today. Okay, this is the roadmap. We're going to use the beautiful slides with and concepts with the terrible expressions. We're going to state them in the far source and far field condition. We will use radiation pattern from a double couple in that condition, and we will try to use this using a sort of the visual representation with a projection that will become what we call the focal mechanism. Then later, but I don't think we will be able to do that today, but so probably we will restart on Monday. We will make a step backward and we will go back again to the concept of an extended fold. And we will consider what is called the Haskell model. That is the simplest extended source model that we can imagine. Since we will not treat it, let me just make here a very quick, what is that, chalk. The Haskell model is very simple because we will consider an extended fold with a given length, a given width, and we will consider a rupture process that will start from one side of a fold, it will continue, and then it will stop. So it's the simplest, because it will have just one direction of rupture, just one direction of slip. We will define what we call rupture velocity, and it will be constant. So everything is nice here, and this is the simplest extended fold model that we can imagine. We will use it to derive what we call the source spectrum, and that will be very important. Okay, but today we have to imagine to be so far that all what is happening here is in a point, and we have a double couple in a point. So we will consider a point in space that will radiate with a given kinematic time, and the only kinematic time that is left here will be rise time. So the time necessary, there is the slide in a couple of minutes, so you will see it. And we will use the radiation in the far field condition from a point source. This is what we have to develop today. So let's go back to the screen and let's make a recap of what we did. The summary is here because we considered a surface. Let's imagine it's a plane, and the plane can be described by strike, dip, and the mechanism with a slip vector. The slip vector is perpendicular to the normal of a fault. Pure shear dislocation. Then we can integrate it. We can consider an average dislocation model with a given slip on a given area and with a given time, and this is called rise time. Then the equivalent body force that can represent the radiation of this mechanism is a pure double cut representation theorem. And for a pure shear dislocation in the far source condition, what we are left is this very powerful expression. It represents the convolution of a moment tensor that in this case is symmetric with zero trace, and one of the eigenvalues is 0. It's a pure double couple. Then we have to convolve the 6 elements, independent elements, that we can diagonalize. And if we diagonalize it, we are left just with plus m0 minus m0. And m0 is the scalar moment, rigidity modulus times the area of a rupture times the average slip, convolved by the spatial derivative of the Green's function. What about the Green's function? Okay, and this is the sketch, the final sketch that we used at the end of the representation theorem. A rupture on a fault plane, it can be represented by a moment tensor, a very simple one. We can diagonalize it like this. The axes that are the principal axes represent traction, compression, null. And these are the 3 different representations: slip on a fault, principal axis, moment tensor. Equivalent body force, principal axis. Then we developed the beautiful theory of the Green's function for elastodynamics. The complexity was arising from the fact that we had to consider a delta in time, a delta in space, and delta in direction. And we solved it. And we found near field and far field. The far field was nice because it was containing what we were waiting for: a P wave and S wave, spherical waves, and then they are radiated according to a radiation pattern. And for a single force, the radiation pattern was simple: sine and cosine for P and S respectively. But the Green's function is not enough, because we have to take its spatial derivative, because we have to consider a couple of forces. And the spatial derivative means that we are considering a force in one direction and an arm in the q direction. And with this additional operation, the expression that we're looking for is on this slide, that is one of the conclusions of the last lecture. There are 3 terms, and they can be distinguished according to the rate of decay in space. Cycles are here, and this is what we're waiting for, P and S. Good. Then there are additional terms, a little bit more complicated. but they are decaying faster, going far from the source. For today, we will neglect it and we will concentrate on this. And we're going to develop, in a very simple case, infinite, homogeneous, isotropic, elastic space, so with just lambda, mu, and rho, so just alpha and beta. What is the radiation pattern that we're waiting for a pure double couple? Now, the answer to the question that I was asking you as a sort of a homework is actually contained here, because I was telling you, yeah, everything is fine here. This is what we are waiting for in the far field, but there is the time derivative of, let's call it, the source time function. What is coming from the derivative? Actually, it's coming from a spatial derivative. Because if you use the chain rule to compute the spatial derivative, you're getting a direction cosine, and then you have a derivative of space with respect to time. That is the origin of this dot here. And that's why in the Green's function, the pure Green's function, just one force, there is no time derivative. If a singer is singing, what you're listening to the place where you're putting your receiver is the singer. But if you're going to compute the spatial derivative, you're going to listen to the time derivative of the song. Let me show to you a piece of literature where you find this demonstration. But I told you, the answer could be in 1 second, because it's related to that spatial derivative. If you want to be a little bit more accurate, this is the development when you consider not only a force, but a couple. And this derivative here, respect to space, it's coming here. Because when you take a couple with the arm and you use a Taylor expansion, what you're getting here is this derivative. So that's the origin. The origin of that time derivative is in the spatial derivative. So in the fact to compute the contribution of an f and the contribution of the other f, but a little bit displaced in space because we have an arm. Okay, that derivative is causing the time derivative when you use the Taylor expansion. And so that is why here you have, that's not a fly, it's a dot. Okay, so that was the solution. Okay, let's start with today's topic. It should be a relaxing one, but we cannot relax. So the relaxing part is containing this wordy slide. And what we're going to consider today is the radiation pattern. Okay, let's take our beautiful, how to say, theory that we developed. From the representation theorem, we have this expression here. From the Green's function theory, we have computed what are the terms of this. And so if we go in the far field for a point source, what you're getting here is this beautiful expression. We're waiting for a P wave, for an S wave, spherical waves. Their amplitude is dependent upon the relative position What I'm trying to say is that the relative position of the receiver respect to the source position will decide how much the amplitude will be. Why? Because these two angles here are referred to the source. And so according to his position, we can get a strong P, a null S, a strong S, a null P, and so on. And then, as I was telling you, the information about the time that we're going to get is the time derivative of what's occurring at the source. So for example, two very simple but important sketches here. Let's imagine that the sleep function is 0, and then sleeping in such a short time that the function is like a step. Then what we are getting, it will be a delta. In a more realistic fashion, let's imagine that our sleep is occurring in some time. Okay, this amount of time is called the rise time. The time necessary for one point on the fault, but today it's a point, so it's what we're left with. Okay, if it is taking time tau, then what we are getting at the source, at the receiver, it will be a boxcar with duration tau. That will become important on Monday. Now, checkpoint. Are we together?
Yes.
Yes,
wow.
but I don't know about the order. It's like we are seeing you very slowly. I think I don't know about the order. If it's only me or.
It's true. I see the same.
Very slowly what? The transition between slides?
No, I think it's the network. When you are speaking, sometimes it's the network cut off. And
sabotage is occurring here. I don't know, apparently that the strength of Wi-Fi here is good. But okay, don't move. Look at the slide now. We don't have to be fast. But on this slide here, there is a sort of a recap of what we discussed until now, using far source and far field condition. Let me ask you again, and let me stop sharing, just to be sure. Are we on the same rope? Okay? Okay, let's try to go on. Dung, I would like to receive a yes from you, or no?
Yes.
Okay, that's a yes. Good. Let's restart. Okay, what's next? What's next is that now we have to imagine an image of what's going on. These two slides here are coming from the textbook that I was suggesting you if you need one, but this time was session, just to relax you and show you that actually what we are discussing now is not about rocket science, it's something classical now. And taking now into consideration first the P wave radiation pattern and using this, let's say it's a sort of a spherical reference system, but it's not the center of the Earth, it's the center of the source. So the position will be at a given radial distance, and its position will be decided by two angles. We can imagine that they are like longitude and colatitude, like for the three modes of the Earth, but now again, the center is not the Earth, it's the source. Okay, if you imagine to combine this geometrical information, what we are going to get is a 4 lobes radiation pattern like this. Now, what is the information that is carrying on? Well, for P waves, it has to be a push or a pull, according to our position, according to the orientation of a double couple and our relative position. So the time information is related to the time derivative of the slip function and so on. And for P Wavefield, since it's a longitudinal compressional wave, again, the information is big plus, big plus, big minus, and 0 along these planes. And these planes actually are nodal planes. In principle, on those 2 planes, there is no P radiation. We're not getting anything if we sit there. And one of them is the fault plane, the other one is the auxiliary plane, T and P. From the point of view of the radiation itself, we cannot distinguish them. This is due to the symmetry of the moment tensor. Okay, what about the other one? Actually, we're going to develop the first one, but what about the other one? Well, it's carrying information about S waves, and we know that S waves are transverse. So their information is carried on a plane that is perpendicular to the direction of propagation. That's why, using this reference system, they have 2 components. One is running along theta, and the other one is running along phi. They could be very strong in one direction here, very strong in the other direction on the opposite, and then we have 2 points, not planes, where the radiation is 0. And actually, they can be called nodal points. And they correspond now to the direction of the principal axis. As I was telling you, please remember that here, in this very simple, elastic, infinite, isotropic, perfectly elastic, whatever, elastic domain, here we have beta cube, and for P, we have alpha cube. And you do remember that beta is the square root of mu over rho, alpha is the square root of lambda plus 2 mu over rho, so beta is less. That's why they are called S, secondary waves. And so, on average, S waves are larger than P waves. Good. This is again a sort of a recap. We're just looking at the same thing with a sort of the geometrical vision. Let me, okay, and I think, no, okay, let's consider also these 2 slides, then I will show to you an animation. Again, if you imagine to consider the same source that we developed during the specific case for the representation theorem, if you remember, there was a strange fault with a slip in this direction, okay? So we discovered that its body force equivalent is a double couple oriented along X and Z. That's the radiation that we can see from the side. So just looking at a given phi and running with theta, you see how complementary P wave radiation pattern, S wave radiation pattern, and this is with vectors. So this is another vision. This is another vision, just to remember you, this is for a different, the DP is 45, but this picture is nice. Why? Because it's showing us, and let's remember that the radiation pattern is a sort of the antenna profile for a seismic wave emitter. And let's remember that it's a 3D beam, sort of beamy shape in space. How P wave and S waves can be compared with the distance. So one of the first animation that I would like to share with you is this one. I'm not suggesting it because I'm a specific fan of Mathematica, but this is free. The demonstration can be seen there for if you can see this. Oh, my internet connection is on.
Yeah, hello. Can you hear me? The network.
Do you hear me?
Right.
Yeah, no, we couldn't hear you. The internet connection was.
Yeah, we couldn't.
We couldn't hear you.
Oh my. Let me stop sharing.
So please turn off your microphone.
Kunza, turn off your microphone.
Sorry guys, but here the Wi-Fi seems to be okay. The power appears to be very strong. Evidently it's not. Do you copy me?
I can hear you, Prof.
Yes.
Right now, no.
Oh, we can't hear you well, sir.
You copy me?
I am copying you, Professor.
Yeah, copy.
Right now,
I did
yes.
nothing. Okay, I did nothing. So it's turbulence in the radiation receipt and transmission of something. Okay.
Fabio Romanelli's network bandwidth is low.
The network is slow.
Okay, let me prepare a plan B.
That's fine.
Let me try to use a different thing here. Personal hotspot. Okay, let me try to use
Your hotspots for something.
Okay, do you copy me?
Yes, we copy, but it breaks sometimes and it comes on and off.
What about now? I changed totally my connection. I've just made the revolution. I'm using my mobile phone.
Okay, talk again. Let's see. Let's see if it will be continuous. Talk and let's see if it will be continuous.
Okay. What is worrying me a little bit is that I've lost Tarek.
I'm still here. I'm still here.
Okay. Do you copy me?
Yeah. I think
yeah.
It's good now.
Okay. I'm using my poor mobile phone. Okay. So let's try if it's working better. Plan B. We have to be ready for focal mechanism everywhere at every time. Okay. Let me try to share my screen again. And okay. Do you see something?
Yes.
Yes.
Yes, yes.
Okay. So if you want to download the same this is free, just a way to visualize it. What you can do is to change the strike. You can change the dip. You can change the strike, actually, not the strike, but the slip angle, what we call the rake. And you will see that this four-lobed radiation pattern is going to change in space, but its shape, it's always the same. You can imagine also to have it fixed and to take your receiver around the source, so it will be the same. This is for P, and this is for S. So this is what we are visualizing. Now, that's the message to take home. We have this radiation pattern. Now the question is, can we use it to produce some nice representation? And this is, again, some slides are just a sort of a history repeating here. And it's one of the first recap. Fault plane, we use it, we consider it so far so that we can squeeze the information in one point. In that point, we have an equivalent body force that is a double couple. We consider the Green's function. We consider the radiation of the Green's function. And now we have a four-lobed radiation pattern in space. Why I'm using this old-fashioned slide here? Because there is a sphere around the source. Now we can imagine to use this image of a sphere around the source. And actually, if you imagine, it's just a way to rotate this in space. And imagine, okay, if we have a network of instruments distributed over the surface of the Earth, what should we get from this radiator, from this seismic radiator? Well, according to our position, we could get different messages. For P waves, and this means the first arrivals, we could wait for a big push, a big pull, something in the middle, and along the projection of two planes, zero radiation. Can we use this? And again, this is the same vision, but coming with a little bit more of detail from another textbook. Why I'm showing this repetition? Because just to show to you that this image is pervading all, let's say, not elementary, but all seismology. So I'm using here the pictures coming from Stein and West Session, Lay and Wallace, Aki and Richards. So all the textbooks are showing the same image here. And from this image, it's time to get an idea, P and S. Now let's consider P. So the key word until now is double couple, far field, radiation pattern. And I've been showing you so much times this sphere, but now it's time to represent it in a better way. And this is the sort of a summary of what we're going to do. So if you are going to listen in your future, the word seismic beach balls, actually it's a sort of a jargon of an easy translation of what we can call the representation of the focal mechanism. But please remember, since now you are an alpine guide, or an Andean guide, or a Himalayan guide, now you know where these are coming from. Now, what is the idea? It's just to represent this 3D radiation pattern in a 2D picture. And thus, the passage is to use a projection. And the projection, what's going to do? Well, a plane will become a line. A line will become a point. And lines could be, for example, the ray paths of the waves that are leaving the source. Now, please remember, that a ray or a ray path is not a physical object. It's a visual object representing the direction perpendicular to the wavefield, to the wavefronts. But it's a very useful idea because we can imagine, like in optics, we can imagine the trajectory of energy. So we have two lines, two families of lines. The first one will belong to trajectories of waves. The second family, that is actually a small family, will contain the vectors. Which vectors? Well, let's remember that we had a fault at the beginning. So strike, a dip, and rake, or T, P, B. It's the same. Okay, those three vectors will become 3 points. While planes, like a fault plane, it will become a line, and according to the projection, it will be mapped into a curved line. Okay, let's try to put in practice this idea here. For example, let's try to represent a plane. Well, that's quite easy because we have to imagine now the sphere that is surrounding the fault plane. Okay, we have to imagine the surface of the Earth that is cutting the sphere. Let's imagine for now that is emerging at the surface. And now we take the lower part of the sphere and we look at it from the top. It's a convention. We could also imagine to take the upper part. But for seismology, what's quite intuitive is to take the lower part. And you have to imagine, I will show to you just the beginning of a very nice video that we can find on YouTube. And so you will appreciate this idea. But for this slide here, let's imagine that we have a sphere, we have a plane. If you look at it from the side, we have a line like that. But if we look at it from the top, the lower part of the sphere, that plane will become something like that. Okay, that's the game that we can play for a plane. Just a word that is coming from not my cup of tea, but maybe some geologist is much more familiar with these things. Please remember that this idea can be developed using many projection styles. Usually, what we are adopting for focal mechanism is the stereographic projection. Why? Well, because it's useful and it's conserving angles better than areas. So the idea on how to project lines and planes in a sphere can be developed in many ways. The one that we are going to adopt, that is usually adopted, is what is called the stereographic projection. So with these tools in hand, we can now see how to put in practice this idea, first representing a fault, for example. Okay. Please, you can relax a little bit because, you know, when I was a student, we were forced to do these experiments by hand. By hand means that we had to print this map there and to play with the pin and to make this rotation. Now computers and softwares are doing this in an automatic way. So you can relax, but not totally relax, because remember that advanced inversions need the knowledge of what we are doing here. So let's imagine that we're going again to play with a piece of paper, like in this slide here. So for example, let's imagine that we have a fault, and the fault can be described by two angles, the strike and the dip. The strike is telling us, okay, what is the angle to the north, and the dip how it is inclined respect to the free surface. So that's the image with the sphere. And to plot this information here on a stereo map, on a stereo net, what we have to do is first to take the amount of, for example, in this case, 109 degrees from the north, and we plot this point here. Then we go back, and the dip can be measured here. You see, you take from here, you take 55, and you're done. You re-rotate it by 109, that's easy. So if you know a fault, it's easy to plot it. Step number 2. What about a vector? Oh, for the fault, we have an important vector. It's the slip vector. It's the direction of the relative motion of the hanging wall respect to the footwall, if you remember. Now, for example, on this fault, let's imagine that the rake is 20 degrees. What we have to do is to do the same rotation as before, measure 20 here to put it back, and now the fault plane with a mechanism on it is becoming a line plus a point. Easy. But actually, what we want to do is not the direct problem. So we know the fault, we know the mechanism, we plot it. That's too easy. What we want to do is from the information to get the fault and the mechanism. So it's a sort of an inverse procedure. So in the direct approach, this geometrical game, it's quite easy to be played. It's a little bit less easy to play on the other side. What does it mean? From data to this. Now, what are the data? Okay, you could say seismograms. And yes, actually in seismology, data is seismograms, no way out. And you can use, someone is saying is that you can need all the pieces of a seismogram, but actually you can use the whole waveform, you can do some filtering, you can do many things there. You can do what is called full waveform inversion. But what we are going to do today is just to use one piece of information, is the polarity of the first arrivals. First arrivals, P wave. Polarity, up or down. This is the piece of information that we are going to use today. And how to use it? Well, we have a tool now to interpret it, because we know that they should live according to 4 quadrants on a sphere, with pushes and pull. So now it's again a matter of convention. For example, and this is what we're going to do. Let's imagine that we are making phone calls after an event to all the people in the seismic stations around the world. So we phone and we ask, okay, can you tell me what is the direction of your first arrival, the polarity? Is it plus or minus? Hoping that the instrument has not reversed polarities, it happened. Okay, you're going to collect a set of information of pushes and pull or nothing. Sorry, the first arrival is pretty much nothing here. Okay. Now, with that piece of information, you have to imagine to put it back, to project it back to the source, and to depict it. So if we're going to get a push, a plus, so it's a compression up, we have to imagine that from the point of view of the source is a pull, because it was pushing. And vice versa, a pull at the receiver, if you imagine to project it back to the source, okay, that will be something that was going inside the source. So please remember every time the duality between receiver and the source. Okay, now, with this idea in mind, let's develop it further. This image here, I added this image here because it's coming from Steinway session textbook, just to relax you and to tell you that if you want, you can find many pieces of this information on that book. And so, for example, again, you can measure here the azimuth of a fault, the dip of a fault, and so on. So it's easy to plot different faults with the same strike that is 0, for example, with different dips. You will see these are different lines. It's just an example to show you how simple it is. And for example, this is something that is very similar to the exercise that I proposed you, but just following Steinway session textbook, that again, I suggest you to use it as a sort of a reference. So you can find that information. Now, what about the normal of a plane? Okay, if we have a plane and we use it during the representation theorem, you do remember that we have two angles that can define a plane, or its normal. Okay? Now, the normal of the plane actually can be called, now imagine this normal that is getting out from the plane and it's touching the sphere, that will be called the pole to the plane. So the projection of that vector, remember a vector becomes a point in this representation, that will be a pole. Okay, so if you have a circle on this map that are passing through this pole, it means that all these planes will be perpendicular to the initial one, because they will be parallel to the normal. Just to let you imagine how things are projected using this convention here. Let's proceed with the final piece of information. Now, what about a ray leaving the source? Well, we have to imagine that a Wavefield is a sphere. So, yes?
Sorry for the interruption, Professor. What did you say? What about the... I didn't hear you.
Okay, about this slide here.
2 seconds, just wasn't one word. What about?
Okay. Let me try to repeat what I was saying here. Now we have to imagine that from the point that is where we are considering that the source is, a wavefront is living.
Okay. Thank you.
Now a wavefront is living in over all a sphere. And we can imagine a set of rays from this sphere. Every ray, that means one point in this projection, will represent a ray leaving the source with a given coordinate. And to trace this ray that is leaving the sphere, we have to use two angles. One is giving the azimuth of the ray, and the other is telling us how deep it was, this ray. So two angles to represent a point, and now this point has not the physical meaning of being an axis of something or a normal to a plane, but this is a ray that is leaving the source. That ray will be plotted as a point. So in the direct world, we performed everything. We have a fault, two angles, or a line. We can imagine a mechanism. We had the slip on that plane. And now we can also imagine all the rays leaving the source. They will become points. Let's be direct. Now it's time to imagine to do the opposite. To take all the information around the Earth at the receivers, phone call, is it plus or minus? And then we adopt a convention. If it is plus, or if it is pull, plus or minus on push and pull, we will plot them with different colors, black and white. So in principle, if we had infinite receivers deployed over every point of the surface of the Earth, we would have, well, infinite dense information, and then we could map a beautiful pattern of black and white there. In practice, we don't have infinite information, but we have some information. We found plus minus, black or white, and the game is to take it back around the focal sphere, and the focal sphere will be seen cutting it, looking at the lower hemisphere and looking from the top. That will be the beach ball. Wait a second, because it's not enough yet. Same concept on this slide. It's redundant to show you that the same thing is not only on my slides, but also on the Steinway session, if you want. Now, this is the critical and final step. How to trace it back. Okay, let's go back to, well, usually, to wave physics, or to your previous knowledge. When I was doing the wave physics course, I was speaking in one lecture about seismic rays inside the Earth. I'm sure that you did the same with Lapo, who is really an expert about rays in the Earth. But in any case here, using Snell's law, and Snell's law is in your pocket. Wait a second. Is Snell's law in your pocket? The connection should be bad. I don't get any sound from you.
I think so. Yeah.
Okay. So, but it's not quantum mechanics. It's not a wave function that could be yes and no. I mean, Snell's law is telling us that whatever trajectory a ray is doing, it has to obey this law here, that the ratio between the sine of the angle, of the incidence angle, over velocity has to be constant. This is valid in flat geometry. If you are in spherical geometry, you have to multiply by r. This is called spherical ray parameter. By the way, to trace the rays back to the source, in principle, is easy, provided that we know two things. Can you tell me which ones? Okay, let me share again. How to do this? Because now you see
Time.
The distance.
One, that's the first, the position of the source compared to the receiver. Actually, in the Earth, in a spherical Earth, we should know the angular distance. But yes, the first one is to know where the source is. So in this case here, in the direct problem, okay, let's imagine that we have a source here with its mechanism. Let's take the focal sphere, let's cut it, let's look from the top, and let the rays to propagate from here. Okay, bingo, we go, we take a phone call, and we can say them, okay, my friend, you got a plus, you got a minus, you got nothing. But in the real problem, we have to call, ask, and project them back. So the first piece of information that we should...
Professor,
yes?
it depends on the position of the receiver. It's if it's near the source, we consider it flat. So we consider we don't consider the sphericity of the Earth.
No. Okay, that's fine. This cartoon here actually is showing, but remember, we are using a point source approximation. So we have to imagine
far, we are far, okay.
That we are far. So in some cases, for global seismology, you have to take care about the sphericity. That's fine. That's not the problem. But definitely, we should know where the source is. And this is a piece of information that is coming from independent studies. And remember that for the position of the source to be identified, we have uncertainties in the real world. So every time that we are doing this beautiful inversion, remember that there are uncertainties. But let's imagine that we know where the source is. But now to trace the ray back, we need to have also another piece of information, how the Earth is made. Otherwise, we cannot trace the rays back. We have to know the Earth's structure. But okay, we know it. Oh, we don't. We know for far distances, we can use a sort of a global model, and we can do that inversion. But please remember that also in this case, some uncertainties can come from this assumption. But if we know the distance, and if we know the structure of the Earth, we can use these tables here. These are a piece of, let's say, all the tables. They are called the Jeffreys-Ballen travel times. And if you know the distance, and you are getting there, and you have the time, and you have a clock, okay, now from that position, from the relative position, you can take the takeoff angle. This angle here can be traced back to the sphere, but please remember, it's coming from the assumption to know the Earth. Okay, let's imagine that we are so powerful that we know that. Then what we can do is to take that information, trace it back, create the cloud of points of information around the sphere, cut it, and look it from the top. That's it. So, for example, and now I will show to you one animation and one very nice movie. In practice, the story is a little bit more difficult, but there are many routines that have been developed in seismic agencies. And what they are doing are just doing what I was telling you, collecting the information from a seismic network, a global one, distance, takeoff angle, trace the information back around the source, put in blacks, put in whites, divide them with lines, cut and look. That's it.
Professor.
Yes.
The take-off angle, I didn't get it well. What
it's
is
this.
The take-off?
Actually, it's this.
43 here?
No. This is an example. This is just an example. Wait a second. I was telling you.
So
you have to...
it's a distance. It's an angle between the direction of the direction of.
No. Wait a second. You have to imagine to have the point source. You have to imagine to have a sphere around it. From that point, wavefront is starting, the P1, okay? Now, what is the wavefront? Every point of a wavefront is representing a ray. Now, these rays will leave the source, and according to the structure of the Earth, they will make some angles. These angles depend upon the structure of the Earth. Now, the structure of the Earth will decide what is the future of this ray. Okay?
Okay, get it.
Now we have to take the time back. At this station, we got a ray. Now, we assume to know what is the structure of the Earth. We have the distance of a source, this angular distance here. Knowing the structure of the Earth, now from this information here, we can trace this information here. Okay? That is the takeoff angle. So this information will be mapped like this as a point. Oops, pardon. It will be mapped as a point. A point. Now that point will have a black or white according if it is a push or a pull. So the result is that on this stereo net here, we will have a series of dots of blacks and whites. And we have to separate them with two great circles in this plot. Those two circles, those two lines, curved lines, those two great circles there will be, one will be the fault plane, the other one will be the auxiliary plane. But we will never be able to distinguish them for the symmetry of a moment tensor. What we know from the theory that we developed, that they have to be divided into 4 quadrants. And this is the idea. So once you perform this, what you get is this information. Let's imagine that we have found, according to the distribution of blacks and whites on that stereographic projection, that these are the two planes that are separating whites from blacks. Now from this, we can read the information that we need, because we have this plane here that will have a given strike, a given dip. We have the other plane that has a different strike and a different dip. The rake can be found. Now that's a little bit more tricky, because we know that the axis of T will be attraction for the source, right? Traction for the source means that for the receiver, it will be a push. Pressure for the source means this. For the receiver, it will be a pull. So actually, the T and P dots, they have to be in the black zone and in the white zone, respectively. And so we will have this separation in black here, white here, if the situation is T and P. If we reverse the mechanism, this will be P, this will be T, and this will be in the white. Now you have to wait a second, because this piece of information is going to be developed in the next minutes with easier examples. Now, once you have P and T, please remember that they have to be at 90 degrees between them and 45 degrees between the fault planes. So once you have T and P, you can create this circle here, and from this point, you can measure the rake of the mechanism with the convention that I was writing here. Luckily, all this work now is done on a routine basis. And so we will get immediately the pictures that we are going to see now. But please remember what is the logic beyond it. Now, let's help ourselves with some animations and movies. For example, let me close this and open this. We have to take some time here. Okay. Look, this is another sort of the applet that can be played in Mathematica. And it's allowing us to make some exercises. For example, you can decide to use not the stereographic, that is the classical one, but you can decide to use this. The message is not changing. You can decide to use the upper projection, but please do remember that on standard basis, the focal mechanisms that we're looking in literature are the focal sphere, cut, and looking from the top, the lower one. And you will see this in the movie. Now, if you want to change the angles here, you can play with them. And if you use a dip that is 90, you can get like that. Oh, that's beautiful. Now, if you change the strike, this is what's going to happen. But if you change the rake, okay, let me use it at 90. Okay, now I was using here an amount of slip rake of 90. So it's going to the top or down. It could be a thrust or a normal. Now you see, you don't see the quadrants. You see just two, because we're looking from the top. What is coming up? What's going down? This is the tricky part, but let me show to you the animation that I was mentioning before concluding this part. It's on your Moodle website. And for example, here. So this is, you have to be happy because the homework that I will leave to you today is a nice one. It's, okay, you have to watch this movie. Well, you have also to read the primer that is there. I hope it's going to work. What's happening here? Okay, sorry. Now we will start looking at that. Okay.
When an earthquake occurs, seismologists create graphics of focal length.
Wait. So what we are going to do now is just looking at a couple of minutes of it. Your first homework is to spend 6 minutes in looking at that. It's very nice. And you will see why. Let me go fast here. Because in the first part, it's something that we already developed. But some parts are not, so I'm not joking now. Your first homework is to look at this. Okay, no, I don't want to begin again. Now, we have here some information about what's going on here. I don't want to, okay. Push and pull, now we are looking from the top, a strike slip mechanism. So it's easy. What we will see now is something that we're waiting for. So you see, the push is going to be mapped with black. The pull will be mapped by white. And looking from the top, we have a beautiful division into 4 quadrants. And there is a hint and a question to you, a very easy one. Looking at this plot, can we decide which one is the fault plane and which one is the auxiliary plane? Well, the answer is no, because we have 2 possibilities. Because the same radiation pattern, the same focal mechanism pattern, can be obtained both using this as a fault plane or this, according if it is a slip like that or a slip like that. And you will see this now. There is an audio, I don't want to get it, because this is going to cause exactly the same as this. You cannot distinguish, we cannot distinguish. So remember, this is arising from the fact that the moment tensor is symmetric. Now, this is easy because it's a strike slip and seen from the top. Now, let me go to something more tricky. That is a thrust. Wait a second. Let's be erasing the Earth. So remember your homework. Okay. Now, what we're going to look here, it's a normal mechanism. So we have a fault plane and a slip that is 270 degrees. Look at the representation now. If you put the sphere, and if you consider the motion, and if you look it from the side, you will get the usual 4 quadrants representation, definitely. But the point is that now, what we're going to map is you have to imagine to cut it and looking from the top, as it will be shown just now. Okay. So you see that the dip, well, the strike is, of course, decided by this. The dip will decide how much white there is in the middle. And I invite you to play with that animation. What is important is that since the mechanism is normal one, if you look from the top, you will see a pull down. So it will be the white inside. So a normal mechanism will have a white here. A thrust mechanism will have black there, and that's the end of the movie. You will see it here. If you look from the side, it will be 4 quadrants, but when you project it on the top, you will have black inside. Okay. So that's the way how to distinguish normal mechanisms from thrust mechanisms. This is your first homework. The second homework, and I'm not joking, is to read this beautiful PDF that has been prepared for a grad people in geology. And it's nice because it's giving some very practical hints about, you see, that's it, about what we discussed. It's a very nice reading with some exercises here. This is what we had been discussing. So you see, there is an example on how in practice could appear a distribution of white and black dots on that. And now you have to imagine to try different solutions and to find the best 2 great circles separating blacks from whites. And then you can read that. So there are some exercises here. Now let's go back. So you have this on your Moodle website, as you can see. This is just a reading. I will tell you why in 1 second, but that's it. Let's try to conclude our lecture for today. And the summary is very relaxing because actually the focal mechanisms, the basic ones, will appear into 3 different styles. If we have a strike slip, imagine to look from the top, you will see all the 4 quadrants. If you have a normal or a thrust, you will see something like that with white or black inside, according if it is normal or inverse or thrust. The amount of white and black will depend on the dip of a fault. It's very easy. But please, so it's a very nice representation. And if you have a combined mechanism, you will see a mixture like that. Now, to read very quickly this information is that, okay, looking at this division, you can say strike, normal, thrust. Looking at the direction of these lines, you can have an idea of a strike of the fault or the auxiliary plane. And the amount of white and black here is telling us also the dip. In this situation here, it's a little bit more complicated, but this black dot is telling us what is the prevalent mechanism. That's the summary for today. Now, before concluding, let me tell you two things. The first, what we did today is to use all the information that we developed there, take it to the extreme, so point source, far field, use the radiation pattern for P waves, and to get the representation of the mechanism. So you can call it focal mechanisms, or you can call it, as a slang, beach ball. It's telling us the orientation. Well, it's telling us the mechanism that was occurring on a fault. And this is the general message for today. Two conclusions. The first, they are related. So, looking at the focal mechanisms, we can have an idea of the stresses in that area. At least we have an idea of TBP. So looking at focal mechanisms, we can use them also to have an idea of geodynamics, of the prevailing stress. Remember Anderson theory of faulting that we had been using in the first lecture. And you can develop this also with Karim's course. And so that was the conclusion for today. How to use it? Well, again, a redundant slide here, just to have a sort of a very simple summary with graphs here. But actually, what is joining everything is this. Because you see there that if we have a situation with P, T, and B that is getting out from the screen here, we have to remember, okay, it's P for the source, so it's inside the source. For the receiver, it will be a pool, so it will be white and black here. The principal axis and the fault and auxiliary planes will be 45 degrees, 45 degrees, 45 degrees, 45 degrees. Okay. Now let's imagine to take this situation here, to put a sphere, to cut it, and to look at it from the top. You will get this image or this image. If you look at it from the side, you will have this image or this image. If you rotate it, the general vision will be always like that. So the focal mechanism is also telling us the orientation of the axis, of course. It's reflecting MIJ, it's reflecting PTB, it's reflecting strike, dip, and rake. So you see, all the terrible algebra and physics or maths that we did until now was squeezed in these apparently silly representations. But please remember all the assumptions that we have been doing so far. And this is one example that is coming from a page of a suggested textbook, just to show how it works in practice. So you distribute white and black dots. You find 20 years ago by hand, well, 30 years ago by hand. Nowadays, it's, of course, you have graphical tools to do that. You separate them, you find two great circles, and from that position, you have a hint for the mechanism and the TBP. To conclude, let me show to you some other representations, because what we did for P waves, we can do that also for S waves, and we can do that also for surface waves. In many cases, we can use surface waves. I'm not entering here about the algebraic detail of radiation of Rayleigh waves and love waves, but please just remember that Rayleigh waves are P and SV waves. Love waves, they are SH waves. And so love will be strictly connected to S, while Rayleigh it's a mixture. According to different mechanisms, the radiation pattern will be different. In some cases, it will be four-lobed. In some other cases, for love and Rayleigh, it could be two-lobed. But generally, they are always complementary. The directions where one is maximum, sometimes, usually, well, pretty much always, we have a direction where the other one is 0. So please do remember that if you're going in the future to make some a focal mechanism determination using surface waves in Canada, okay, please remember that the theory can be applied the same, but not looking at the polarities of P waves, but the polarities of first, Rayleigh, and Love waves. So you can do the same, just take into your pocket. Another piece of information that is, I put this slide here to generalize the message. What we did today was to consider these sets here, because remember that when we have a pure shear dislocation, the moment tensor can be symmetric, can be diagonalized, the trace is null, and one of the eigenvectors is 0, like in this case here. And these are the views that we can get from double couples that are representing pure shear dislocations. If you're going to work in Seattle, where you have some, or in Sicily, or in Naples, where some of the events can be mixed with volcanic effects, you may have some explosions or implosions when you have events, for example, decided by magma chambers or with the injection of gases, or if you're going to work with applied geophysics, where you have, I don't know, some tiny explosions, or if you're going to work with explosions in water, please do remember that then the moment tensor has to be different. For example, for a pure explosion, what you can do is to put a beautiful 1, 1, 1 on the diagonal, and you will get a blow. Now, if you get a situation like that, all the rays leaving the source will be pushes everywhere. And so the beach ball for a pure explosion is totally black. If you have a cave that is imploding, it will be totally white. Then there is another mechanism, but I will not enter into these details, that is called CLVD, compensated linear dipole vector. That is, and they are used in, for example, if you are going to study some fracking sources, it's not my word, but if in the future you are going to use it, remember that the moment tensor can contain also those sources. What is the difference here? The trace is 0, but none of the eigenvectors of the eigenvalues is 0. You can distinguish them because they are not touching like the double couples. So please remember that the theory that we developed with moment tensor can contain other sources, from applied geophysics to fracking, okay? Same theory whenever you consider a point source. Final slides for today. So the direction of PBT is telling us about the stress conditions. Well, let's be careful about that in general, because remember from the first lecture that maybe now we are looking at the slip over a fault that has been created before. So we have frictional sliding over an existing fault, and maybe a long time ago, the stresses were different. But the focal mechanism that we're getting as a snapshot is telling us the actual prevailing stress directions. And now what we are going to wait? Well, if we are at a divergent boundary, we are waiting for normal, convergent for reverse, and transport for strike slip. So let me conclude with these relaxing slides here, that if you plot normal faults around the globe, you will get, for example, ridges, oceanic ridges, or some continental ridges, like the very famous, and you can ask Karim about this, the African ridge here, where you have divergent boundaries. Don't imagine explosions there, but the style is associated with normal faults. If you're going to look for reverse faults, well, you can have continental collision or subduction zones. On average, actually, we have a mixture. If you're going to look for Strike slip, okay, you can go to California, or again, transform faults along ridges. And you can use focal mechanisms also along slabs. Okay, this is the ridge, pardon, you see. Inside this continental margin, that is a sort of a divergent one, you have a lot of beautiful normal faults on average. Now, what about a slab at a subduction zone? Well, we can imagine that at the beginning we have compression, so it's thrust. Then later, maybe under gravity or other dynamic forces, part of a slab is detaching. So we may have normal faults at deeper. And maybe sometimes this is stopping. So we're going to have, again, reverse. So we may have different situations here, and focal mechanisms can help us to decide what is the stress condition there. So it's a tool. Okay, this is Haskell model. It's not for today. You have to wait for the source time function. Let me close with this, because I left here for you as a sort of a good night reading this beautiful paper. It was one of the first papers. It's a little bit large. It's really a beautiful paper, and it was one of the first papers in the history to use the concepts of, if you want, seismology with geodynamics. Now look at the time. Oh, for me, it's a beautiful year, but for you, it's a long time ago. Isaacs, Oliver, and Sykes, and they decided the order by lot. It's written here, okay? It's very fine. Published on JGR at the time, this paper with this title, Seismology and the New. Well, that was new because it was the first time that there was something that was confirming tectonics. Okay, geomagnetism, but seismology here. And if you look at these beautiful pictures, there is one that should demonstrate you why this was important. Oh, it's funny, seismology without any formula here. Wait a second. Okay, this is the beginning. You see, it's not yet the actual focal mechanism representation, but the concept is there. Slip, axis, you know, if you imagine to put black and white there, that's the focal mechanism as seen from the side. So that's it. So to use focal mechanism and seismology, and in that time, instrumental seismology was really at its most. Remember, instrumental seismology started just at the beginning of the 20th century, not first, not before. And in the 60s, there was the boom of instrumental seismology for two reasons. Computers, well, not the modern ones, but the first machines that could do transform computation and whatever. We can smile today, but they were really a revolution. And the second is a little bit less, well, it's more tragic as a reason, because there was Cold War. And so seismic networks had been developed almost everywhere in the world, not to study seismology maybe, but to study nuclear explosions. So there was, in the 60s, there was really the beginning of the modern instrumental seismology. We'll take a look to it on WET very quickly to go towards magnitude. So just to show to you that what we have been discussing today left a deep signature also in tectonics. So to recap, my friends, you have all the slides in the lecture. If you go back here, you have your homework. This is very nice, takes 6 minutes. This is a nice reading. And this is something that I'm leaving to you because just to show to you how important it was seismology for, let's call it, all the new tectonics. So I have to salute you because in 7 minutes I have to start an exam session here. Okay, you can find all the slides here. Just stop at the extended fault model of Norm Haskell. And then, okay, nice weekend.
Thank you.
We are going to see again on each other again.
Thank you.
On Monday. And if you have questions, that will be the time to rediscuss them. Okay.
Yes.
Yeah.
Okay. Thank you.
Thank you. Thank you, Professor.
Thank you.
Thank you, Professor.
Goodbye in the meantime.
Bye.
Yeah, okay.
Yeah. Goodbye,
Bye.
everyone.
Bye.